Imagine a future where humanity never worries about energy again. A future where power flows endlessly, cleanly, and abundantly, enough to fuel entire planets, global economies, or even entire civilizations without ever running out. Now imagine that this future depends on one extraordinary idea: surrounding a star with a megastructure to harvest all of its energy. This isn't science fiction fantasy anymore. It's a concept that some of the world's leading scientists believe could eventually become reality. Welcome to the world of the Dyson Sphere. The Dyson Sphere is one of the most fascinating ideas to ever come out of theoretical astrophysics and science fiction. It represents a level of technological mastery so advanced, it borders on godlike. First proposed by physicist Freeman Dyson in 1960, the idea was simple in theory yet unimaginably complex in practice. What if an intelligent civilization could build a structure around its home star to capture every bit of its energy output? Considering our sun produces over 380 septillion watts of energy every second, the implications are mind-blowing. Could such a structure be built? What would it look like? And if it could work, would it solve our energy crisis forever? Science fiction writers and futurists alike have long been obsessed with the Dyson Sphere because it represents more than just a solution to energy. It's a symbol of humanity's potential to evolve into a Type II civilization on the Kardashev Scale, capable of harnessing the full energy of a star. It's the ultimate megastructure, one that pushes the boundaries of what we believe is technologically possible. But could we actually build one? Could a real Dyson Sphere exist in the universe today, perhaps already built by an alien civilization far more advanced than ours? In this video, we'll explore the science behind the Dyson Sphere, how much energy it could provide, the engineering challenges we'd face, what real-world steps we're already taking towards such technology, and why some astronomers believe signs of Dyson-like structures may already be out there. Could we solve the energy crisis forever? Or are we chasing a dream that's too big, even for the future? Let's dive into the heart of the most ambitious power source ever conceived. Where the idea began, Freeman Dyson and the search for stellar power. Long before the term Dyson Sphere became a staple in science fiction and futuristic discussions, the concept was born from a very real and very curious question posed by one of the 20th century's most brilliant minds. In 1960, physicist and mathematician Freeman Dyson published a short but influential paper in the journal Science. The title was unassuming, Search for Artificial Stellar Sources of Infrared Radiation, but what he proposed was revolutionary. Dyson speculated that an advanced civilization would inevitably need more and more energy as it grew. And rather than continue to depend on dwindling planetary resources, they would logically turn to the most powerful and consistent energy source in their system, their star. What Dyson imagined wasn't a solid, sci-fi style shell encasing the sun. In fact, he never described it as such. His vision was more modest in structure but massive in scale. A swarm of orbiting satellites or habitats spread out across the star's orbit, each collecting a portion of the sun's energy. Dyson reasoned that if humanity or any alien race reached a certain level of technological advancement, building such an array would not only be possible, but inevitable. He also proposed a method for detecting these structures, looking for infrared radiation. A fully or partially enclosed star would still emit heat, just not invisible light. That heat would likely radiate in the infrared spectrum, making it detectable by advanced telescopes. But Dyson didn't invent the idea out of thin air. The seed of the concept had already been planted decades earlier in the pages of science fiction. In 1937, British author Olaf Stapledon released a mind-bending novel titled Star Maker. Within its cosmic narrative was a description of a vast, intelligent civilization that had encased its stars in structures to collect all their energy. Stapledon's vision wasn't technical or practical, but philosophical and grand. It painted a universe filled with civilizations far beyond our comprehension, an idea that clearly resonated with Dyson, who admitted Star Maker influenced his thinking. As the concept entered the public imagination, it began to evolve. Over time, people started to picture Dyson spheres as literal shells surrounding a star, a giant hollow sphere with a star trapped in its center. This version became the go-to image in popular culture, despite being physically implausible. A rigid shell that size would collapse under its own gravity or tear itself apart from the immense forces involved. The distances, the heat, the material strength required, it's beyond our current understanding of engineering. Dyson himself later clarified that this was never his intention. He envisioned a swarm of independent satellites or structures, orbiting the star like an enormous cloud, not a rigid sphere. Modern interpretations have expanded the idea even further. The Dyson Swarm, the most practical version, imagines millions, or even billions, of individual solar collectors or habitats orbiting the star in a coordinated pattern. Then there's the Dyson Bubble, which uses structures that maintain their position using light pressure rather than orbital velocity. This statite concept pushes the idea even further into speculative territory, but it also opens doors to new theoretical engineering strategies. There's also talk of Dyson rings, Dyson nets, and even Dyson trees, living spacefaring organisms capable of gathering solar energy. Despite these variations, a common myth still persists, that a Dyson sphere is a solid metal ball wrapped around the sun. It's a striking visual, and one that has stuck in the minds of sci-fi fans everywhere, but it's also the least likely form such a megastructure could take. The truth is far more nuanced and far more technically interesting. Pop culture has had a massive influence on how we think about Dyson spheres. In Star Trek: The Next Generation, the episode Relics features the crew discovering a full Dyson sphere that contains a habitable interior and a star at its center. The idea is portrayed as awe-inspiring, mysterious, and ultimately dangerous. This visual reintroduced the solid shell concept to a new generation of viewers, helping cement that version in popular consciousness. In the video game Halo, the Forerunner civilization created Dyson-like constructs with vast interior worlds. These portrayals, while scientifically flawed, have kept the concept alive in mainstream culture, making it one of the most recognizable symbols of hyper-advanced civilizations. But perhaps that's the power of the Dyson sphere idea. It's flexible, it's scalable, and it's aspirational. It's less about the nuts and bolts of what kind of materials we'd use or how we'd control orbital mechanics, though we'll get into that, and more about where human curiosity and ambition might eventually lead. It represents the next phase in our technological evolution, a bridge between where we are now and the unimaginable future that might lie ahead. So when we talk about building a Dyson Sphere, we're not really talking about one specific design. We're talking about a family of ideas that span decades of imagination, grounded in scientific reasoning and expanded by generations of thinkers, writers, and dreamers. And as we move forward, those dreams are beginning to look more and more like engineering blueprints. Tapping a star, the scale of solar power. To understand why the concept of a Dyson Sphere is even on the table, we need to grasp just how much energy a star like our Sun actually produces. The numbers are staggering. The Sun emits roughly 3.86 times 10 to the power of 26 watts of energy every second. That's 386 yottawatts, or put another way, a 3 followed by 26 zeros in watts. It's a power output so massive that it's almost impossible for the human brain to visualize. Despite this unimaginable output, Earth receives only a tiny sliver of that energy. The amount that actually reaches our planet is just 1.74 times 10 to the power of 17 watts. That's less than 1/10,000,000th of the total energy the Sun throws out in all directions. In percentage terms, Earth intercepts just 0.00000045% of the Sun's total energy. The rest, it radiates out into empty space, unused, untouched, and wasted, at least by us. Now, let's place this in context. The total energy consumption of all humanity in a given year is approximately 580 exajoules. To convert that into watts, this equates to about 18 terawatts of continuous power. Compared to what the Earth receives from the Sun every second, it's minuscule. And when stacked against the full output of the Sun itself, our current global energy usage is like a grain of sand on an entire beach. This contrast is exactly what makes the Dyson Sphere idea so captivating. We're talking about the difference between fighting over drops of water or tapping into the ocean itself. Harnessing even a small fraction of the Sun's total energy output would provide more power than humanity could ever use. It would make today's energy debates obsolete. Oil, coal, gas, nuclear, solar panels on rooftops, all of it would pale in comparison. The Dyson Sphere, or any variant of it, represents the promise of infinite energy, not just for survival, but for thriving at a scale we've never imagined. This leads us directly into the concept of the Kardashev Scale, another essential part of the Dyson Sphere conversation. Proposed by Soviet astronomer Nikolai Kardashev in 1964, the scale is a method of measuring a civilization's level of technological advancement based on its energy consumption. According to this framework, a Type 1 civilization is capable of harnessing all the energy available on its home planet. A Type 2 civilization can capture the full energy output of its star. And a Type 3 civilization can control the energy of an entire galaxy. Right now, humanity doesn't even qualify as Type 1. We're hovering around 0.72 on the Kardashev scale. That means we haven't yet mastered the total energy potential of Earth itself. But building something like a Dyson Swarm would be a defining leap toward Type 2 status. That's why the Dyson Sphere is not just a technological challenge, it's a symbolic one. It marks a civilization's graduation from planetary dependence to stellar autonomy. When people search for explanations of the Kardashev Scale or ask how a Dyson Sphere fits into our future, they're really asking how far we're willing to go in our pursuit of energy independence. The beauty of the Dyson Sphere concept lies not only in its scale but in its potential simplicity. The sun is going to shine for another 5 billion years. It emits a constant, reliable, and completely clean form of energy. Unlike fossil fuels, it doesn't pollute. Unlike nuclear, it doesn't produce radioactive waste. And unlike wind or hydro, it's not dependent on geography. A structure capable of capturing even a modest percentage of the sun's output would transform our civilization into something radically different. It would enable space colonization, planetary terraforming, artificial intelligence expansion, and breakthroughs we can't even predict. So the next time someone asks why we'd even consider building a colossal structure around the sun, the answer is simple. Because it's there. Because it's powerful. And because it offers the one thing humanity has always craved in its quest for progress, an unlimited supply of energy. Not just energy to light our cities or charge our devices, but energy on a scale that could quite literally power the future. Different visions of the sphere, breaking down the Dyson concept. When people first hear the term Dyson Sphere, the most common image that comes to mind is a giant hollow shell completely enclosing a star, like a metal cocoon floating in the void. It's a captivating visual, one that has been cemented into popular imagination by movies, video games, and science fiction novels. But the reality of building such a structure is far more complex, and frankly, far more interesting. In fact, the idea of a solid Dyson shell, while dramatic, is considered by most scientists to be entirely unrealistic with any known or foreseeable technology. That hasn't stopped theorists from breaking the Dyson concept into more practical and plausible variants that bring the idea of stellar-scale energy collection closer to reality. Let's start with the traditional idea, the Dyson shell. In this concept, a rigid, continuous shell surrounds a star at a fixed distance, collecting the full output of its energy across its entire surface. At first glance, it seems like the perfect way to gather all of a star's power. But there are severe problems. A solid shell of that scale would be gravitationally unstable. It wouldn't stay centered around the star, leading to inevitable collisions or collapse. The stress from the star's radiation pressure, not to mention the gravitational pull from external bodies, would tear it apart. And the sheer quantity of material needed to build a rigid shell would exceed anything we could reasonably extract from an entire solar system. Not to mention, it would likely block out the sky for any planet inside it, cutting off natural day-night cycles and possibly even destabilizing the star's fusion process due to interference. That's where the more realistic and popular idea of the Dyson Swarm comes into play. Instead of a single, continuous structure, the Dyson Swarm is composed of countless individual units, solar collectors, habitats, or satellites, orbiting the star in a coordinated pattern. Each unit captures a portion of the star's energy and either stores it or beams it back to a central location. The beauty of the Dyson Swarm is its modularity. You don't have to build the entire thing at once. You can start with a few collectors and gradually expand, much like laying solar panels across a desert. The Swarm avoids the gravitational instability problem since each unit is independently orbiting, much like the planets and asteroids in our own solar system. It's still a colossal engineering challenge, but it's one that seems within the realm of future possibility. Then there's the Dyson Bubble, a more speculative but fascinating version of the concept. Instead of orbiting the star like a swarm, the Dyson Bubble uses structures known as statites, short for static satellites, that maintain a fixed position relative to the star using solar sail technology. These sails balance the gravitational pull of the star with the outward pressure of its light. In theory, statites could be positioned at specific distances to create a lightweight, stable bubble around the star without actually orbiting it. The Dyson Bubble would require far less material than a shell or swarm, but would demand extremely advanced materials and precision control. It's a more futuristic solution, but one that could, in principle, offer high efficiency with minimal mass. To understand how these variants differ, imagine standing above a star and looking down. The Dyson Shell would appear as a smooth, solid sphere, simple in form, yet impossible to build. The Dyson Swarm would look more like a glittering halo, filled with thousands or millions of tiny reflective dots, each moving in its own orbit but forming a collective network. The Dyson Bubble, on the other hand, would resemble a cloud or a shimmering dome, with vast solar sails held in static positions like a web of light. Each version captures solar energy, but they differ dramatically in how they achieve it, how much material they require, and how likely they are to be realized. In terms of energy capture, the Dyson Shell would theoretically be the most efficient, as it intercepts 100% of the star's output. But because it's not physically plausible, it remains a fantasy. The Dyson Swarm could eventually approach a high capture percentage, depending on how densely it's built, and it allows for incremental construction. The Dyson Bubble might capture less energy per square kilometer of collector, but it compensates with elegant physics and the ability to hold position without expending fuel. The choice between these concepts isn't just about efficiency. It's also about logistics, resources, and risk. The Dyson Swarm, while realistic, would need constant coordination and risk management to prevent collisions or orbital drift. The Dyson Bubble, although elegant, depends on material science we haven't fully mastered yet. And the Shell, while inspiring, is likely to remain in the realm of fiction, at least for now. When people search terms like Dyson Swarm versus Dyson Sphere or want to understand how the Dyson Bubble works, they're often trying to separate the fantasy from the future. These design options help ground that conversation in science while still sparking the imagination. Each version tells us something about what kind of civilization we'd have to become to even attempt such feats. And each one takes us a step closer to that dream of infinite energy harvested straight from blueprint to megastructure, the challenge of building a Dyson Sphere. If imagining a Dyson Sphere feels like a dream, then attempting to engineer one brings us back to the reality of just how monumental this challenge truly is. The concept might sound elegant, surrounding a star with collectors to capture its energy, but turning that concept into a functioning structure involves one of the most complex engineering tasks humanity could ever undertake. The deeper we explore the mechanics behind building a Dyson Swarm or Bubble, the more we understand why no civilization, including our own, has attempted it yet. But could we build a Dyson Sphere someday? And if so, how would we even begin? Let's start with the building blocks. The materials required to construct millions, perhaps billions, of energy-collecting satellites or statites would be astronomical. We're not talking about steel and concrete here. We're talking about materials that are ultra-light, super strong, and capable of withstanding extreme radiation and temperature fluctuations. Two materials often mentioned in futuristic engineering are graphene and carbon nanotubes. Graphene, a one-atom thick sheet of carbon, is more than 100 times stronger than steel and incredibly lightweight. Carbon nanotubes offer similar promise, with strength-to-weight ratios that make them ideal candidates for large-scale space structures. But even with these materials, the quantity needed is mind-bending. A single Dyson Swarm could require more raw material than what exists on Earth's crust. So where would we get it? Mining Earth would be inefficient and environmentally disastrous. Instead, we'd need to look outward, toward the Moon, Mars, and particularly the asteroid belt. Asteroids are rich in metals like iron, nickel, and even precious materials like platinum. Some larger asteroids contain billions of tons of usable material, floating freely in space, without the gravity wells of planets to complicate extraction. That's where the field of asteroid mining comes into play. While still in its infancy, this technology is rapidly developing. Several private companies and space agencies are already investing in ways to extract and process raw materials from celestial bodies. Robots would likely be the first miners, programmed to locate, extract, and refine ores on site. These materials could then be used to manufacture satellite components in orbit, removing the need to lift massive payloads from Earth. The key to scaling this operation would be automation. We simply couldn't build a Dyson Swarm using human labor alone. The scale is too vast. Instead, we would rely on autonomous robots, self-replicating machines that could operate in space, build additional copies of themselves, and begin assembling the structure without constant oversight. Artificial intelligence would be crucial here. Coordinating millions of moving parts in orbit requires calculations beyond what any single human team could manage. I would monitor orbital paths, adjust construction strategies in real time, and prevent collisions between satellite nodes. This construction phase wouldn't happen overnight. Depending on technological progress and resource availability, building even a partial Dyson Swarm could take decades, if not centuries. Some estimates suggest that with an aggressive spacefaring economy, it might be feasible in about 200 to 300 years. Others argue that it could take 1,000 years or more, depending on political will, funding, and technological innovation. Either way, it would require a long-term commitment unlike anything humanity has ever attempted. Then there's the issue of heat. The sun emits not only light but also intense heat and radiation. Any structure placed in close proximity would need advanced thermal shielding to prevent meltdown. Radiators, heat-resistant coatings, and thermal regulation systems would have to be standard on every satellite. Managing waste heat would become one of the biggest Dyson Sphere engineering challenges. If we can't redirect or dissipate that energy efficiently, our satellites could become useless, or worse, dangerous. Solar flares pose another major risk. These sudden bursts of solar radiation can damage electronics, destabilize orbits, and fry circuitry in even the best shielded devices. A real Dyson Swarm would need to include predictive AI systems that could detect and respond to solar events instantly, temporarily shifting units out of harm's way or powering them down to minimize damage. Building in this level of resilience would be essential to maintaining long-term functionality. And then there's the delicate dance of orbital dynamics. Imagine coordinating millions of individual satellites around a star, each one needing to maintain its position without crashing into others or drifting off course. The math is complex, and the margin for error is razor-thin. Each satellite would need onboard propulsion, gyroscopic stabilization, and constant communication with a central AI hub to maintain synchronized orbits. Over time, orbital decay, micrometeorite impacts, and gravitational influences from planets or other objects could disrupt this coordination. Maintenance and self-repair systems would need to be built into every unit. Some scientists suggest placing satellites at specific Lagrange points, stable regions in the Sun-Earth system where gravitational forces balance out. Others propose deploying satellites in layers or rings, each occupying a different orbital band to reduce the chance of collisions. These orbital engineering strategies are still theoretical but form an essential part of how future engineers might approach the problem. The complexity doesn't stop at space. Energy transmission is its own massive challenge. Once the satellites collect solar energy, how do we get it back to Earth or to space stations and colonies? One popular idea is wireless power transmission using microwave or laser beams. These would need to be extremely focused and safe, requiring precision targeting and atmospheric considerations. If misaligned, they could cause destruction or lose efficiency. Developing these transmission systems would be a crucial part of the overall design. And yet, despite all these obstacles, the idea remains tantalizingly within reach. With the rise of AI, robotics, materials science, and space commercialization, we're already building the foundational technologies needed. Each challenge we face is daunting, but not necessarily impossible. The same way skyscrapers, airplanes, and space stations once seemed like science fiction, Dyson Swarms may one day move from speculative engineering to historical achievement. So could we build a Dyson Sphere? Not tomorrow, and not with today's tools. But with enough time, determination, and innovation, the engineering barriers may eventually fall. The vision of a structure capable of capturing the energy of a star isn't just a fantasy, it's a blueprint for the future. A future where we no longer extract energy from the Earth's crust, but instead reach into the heart of the solar system itself and take what we need from the source. And while the path to that future will be long and uncertain, one thing is clear. If we ever do build a Dyson Sphere, it will stand as the greatest engineering achievement in the history of our civilization. Mini Dyson swarms and the first steps towards stellar harvesting. When we think about building a Dyson Sphere, it's easy to get overwhelmed by the sheer magnitude of such a project. Millions of autonomous units, endless materials, a structure that spans the orbit of a star. It sounds like something only an advanced, galaxy-spanning civilization could manage. But like all monumental achievements, the journey doesn't begin with the end goal. It starts with small, incremental steps. And surprisingly, humanity has already taken a few of those steps toward building what could be described as mini Dyson swarms. One of the most exciting advancements in recent years is the development of solar sail technology. The Light Sail project, backed by the Planetary Society and powered by sunlight alone, demonstrated how a small spacecraft could navigate space without traditional fuel. Using the pressure of photons emitted from the sun, Light Sail proved that solar propulsion is more than just theoretical. This concept isn't just useful for travel, it also opens the door to energy-collecting devices that don't require heavy fuel loads, making them ideal for long-term deployment near a star. Then there's the James Webb Space Telescope, which may not be an energy collector, but represents a new level of complexity in space deployment. With its massive sunshield, remote positioning, and autonomous calibration systems, Webb showcases how modern engineering can manage delicate, precision equipment operating millions of miles from Earth. It's a case study in the kind of control, resilience, and technological layering that a future Dyson Swarm would require. In low Earth orbit, we're seeing the deployment of solar panel satellites that hint at what's to come. NASA and private companies like SpaceX and Blue Origin are investing in solar arrays for space stations, satellites, and even proposed lunar habitats. These arrays are not just supporting systems in orbit, they're laying the groundwork for long-term space infrastructure powered by the sun. The concept of power satellites is another step toward a mini Dyson Swarm. These are satellites equipped with solar panels designed to collect energy in space and beam it back to Earth using microwaves or lasers. The advantage is enormous. Solar power collected in space isn't interrupted by weather, nightfall, or atmospheric absorption. This uninterrupted stream of energy could revolutionize how we power our planet. Some of these concepts are already in development, with test launches and beam-back demonstrations planned over the next decade. Beaming energy from orbit isn't without its risks and challenges. Precision targeting, safety protocols, and efficiency losses must all be addressed. But the fact that it's being actively researched shows how serious the idea has become. These power satellites could eventually form the outer layer of a growing Dyson Swarm, starting with Earth's orbit, expanding to the Moon's orbit, and eventually reaching closer to the Sun. Projects like Breakthrough Starshot provide another glimpse into the future. This initiative aims to send gram-scale spacecraft to neighboring star systems at a significant fraction of the speed of light, using ground-based lasers to propel them. The technology being developed here is closely related to solar sails and energy transmission. If we can push probes across interstellar space, we can certainly develop methods to station lightweight collectors around our own star. These are the early building blocks of a much larger vision. While we're nowhere near constructing a full Dyson Sphere, these mini Dyson Swarms represent proof of concept. They are testbeds for the technologies we'll need: materials that can survive space, autonomous deployment, remote coordination, energy transmission, and orbital control. Each satellite launched with solar panels, each solar sail that unfolds in space, and each experiment with wireless energy beaming is one more step toward that distant, but not unreachable, goal. The idea of space solar power is no longer confined to science fiction. It's becoming an engineering frontier. As more nations and private enterprises turn their eyes toward orbit, the dream of building a scalable, modular network of solar energy collectors is beginning to look less like fantasy and more like the next chapter in humanity's pursuit of infinite energy. These mini Dyson Swarms are the spark before the blaze, the blueprint before the revolution. And if we follow the path they're drawing, we might one day find ourselves living in a world powered directly by the sun, not just from afar, but from orbit. Alien megastructures and the mystery of Tabby's star are as captivating as the idea of building a Dyson Sphere is for humanity. There's another, more mysterious angle that fuels the imagination: what if we're not the first to attempt it? What if some distant, advanced civilization already succeeded in constructing such a megastructure around its own star? For decades, astronomers have speculated that one way to detect intelligent extraterrestrial life is by searching for the massive energy footprints that a Dyson Sphere would inevitably leave behind. The idea that we could spot alien megastructures in deep space has shifted the Dyson Sphere from a theoretical engineering challenge to a powerful tool in the search for intelligent life. This speculation came rushing into the public spotlight in 2015 when astronomers analyzing data from the Kepler Space Telescope stumbled upon something truly strange. The object in question was KIC 8,462,852, now famously known as Tabby's star. Unlike other stars that dim in regular, predictable ways due to orbiting planets, Tabby's star exhibited highly irregular dimming events. It would drop in brightness by as much as 22%, which is vastly greater than what even a Jupiter-sized planet could cause. Even more curious, the dimming didn't follow any orbital pattern. It was erratic, deep, and completely unprecedented. The mystery of Tabby's star sparked a wave of scientific curiosity and public fascination. Natural explanations were considered first: dust clouds, swarms of comets, or other stellar phenomena, but none of them fully accounted for the observed dimming. That's when the idea of a Dyson Sphere entered the conversation. Could we be witnessing the partial transit of a vast structure, or even a collection of satellites, orbiting the star and occasionally blocking its light from our view? This wasn't just wild speculation. It was considered serious enough for scientists to begin investigating further. Enter SETI, the search for extraterrestrial intelligence. Researchers began scanning Tabby's star for any signs of radio signals or unusual emissions that might indicate technological activity. While no direct evidence was found, the case was compelling enough to rekindle interest in searching for alien megastructures across the galaxy. One key method SETI uses is to look for infrared excess in stellar systems. A Dyson Sphere, even if it blocked most of the visible light from a star, would still radiate heat, just not in the visible spectrum. That excess heat would appear in the infrared, making it possible for telescopes to detect it from light years away. The logic is simple. If you see a star that's unusually dim in visible light but unusually bright in infrared, you may not be looking at a natural object at all. This brings us to the Fermi paradox. The paradox, named after physicist Enrico Fermi, questions why, given the vastness of the universe and the high probability of intelligent life, haven't we detected any signs of alien civilizations? The concept of Dyson spheres adds a provocative layer to this puzzle. If advanced civilizations do exist and eventually require more energy, wouldn't building a Dyson Swarm or sphere be a logical next step? If so, shouldn't we be able to spot at least a few of them out there? One possible answer is that such civilizations are rare, or they reach a point of technological development and self-destruction before ever building one. Another possibility is that Dyson spheres exist, but we've been looking in the wrong way. Maybe they're built in ways we can't detect yet, or maybe they're in galaxies too distant for our current instruments to observe. Still, researchers have scanned thousands of galaxies using data from missions like WISE, the Wide Field Infrared Survey Explorer, looking for signs of artificial heat signatures. While no definitive proof has surfaced, several galaxies have shown strange, unexplained patterns of light and heat that continue to be subjects of study. The idea that alien megastructures could be out there is controversial but thrilling. It opens up an entirely new way of thinking about life in the universe. Instead of waiting for a radio signal or a flying saucer, we could be searching for the footprints of galactic-scale engineering. These would be civilizations that have moved beyond planetary concerns and are actively shaping their solar systems, possibly even harnessing energy at a scale that we can barely comprehend. For those searching phrases like Tabby's star Dyson Sphere or alien megastructures, the fascination lies not just in the hope of finding extraterrestrial life, but in understanding what a civilization like that would look like. Would it be peaceful or hostile? Would it leave its mark boldly, or operate in ways too subtle for us to detect? Would we even recognize their technology if we saw it? Tabby's star remains a mystery. The natural explanations haven't fully satisfied the scientific community, and the alien theory, while not confirmed, has not been completely ruled out either. It stands as a tantalizing case study in the growing field of techno-signature astronomy. It reminds us that the universe is filled with questions we haven't yet answered, and that some of those answers might come from the places we least expect. Whether or not alien Dyson spheres exist, the search for them has already expanded the way we think about life beyond Earth. It encourages us to consider not only if we're alone, but if others out there have already solved the problem of energy on a cosmic scale. If so, the Dyson Sphere is the double-edged star, risks and rewards of unlimited power. The dream of building a Dyson Sphere isn't just about science and engineering. It's also about what kind of civilization we want to become. On the surface, the idea of infinite energy sounds like an unqualified good. Who wouldn't want a future where energy is limitless, clean, and free from the environmental costs of fossil fuels? But as with any technological leap, there's a darker side to consider. A Dyson Sphere could represent an energy utopia, a world where scarcity is eliminated and every human need is met. Or it could become an existential threat, a concentration of power so extreme that it reshapes society in unpredictable and possibly catastrophic ways. One of the most pressing questions is who would control this immense power source. If humanity were to succeed in constructing a Dyson Swarm or Bubble, the energy output would be thousands or even millions of times greater than our current global consumption. Would that power be shared equally among all nations and people? Or would it fall into the hands of a single entity, whether that's a global government, a corporate monopoly, or a powerful alliance of spacefaring nations? The ethical dilemma is real. Energy is not just a commodity. It's a lever of control. And when one group controls the energy of a star, they essentially control the future of civilization. This concentration of energy raises another concern. Could a Dyson Sphere be weaponized? Theoretically, yes. If energy can be transmitted wirelessly through lasers or microwaves, it could also be redirected as a weapon. A misfired or intentionally aimed energy beam could devastate cities or disrupt satellites. The very infrastructure designed to uplift humanity could also be turned into the most destructive tool ever conceived. The ethics of future energy aren't just about fairness. They're about responsibility and accountability in a world where the consequences of misuse are too great to ignore. There's also the risk of overdependence. A society powered by a Dyson Sphere might abandon other energy systems entirely. That creates a dangerous single point of failure. If something were to go wrong, whether from a solar flare, a structural failure, or a cyber attack, the entire energy grid could collapse in an instant. Unlike today, where energy comes from a mix of sources, a Dyson-powered society might not have a backup. Redundancy would need to be built into every layer of the system, and even then, we'd be placing our civilization in the hands of a singular technological monolith. Some futurists argue that the benefits outweigh the risks. With unlimited energy, we could transition to a post-scarcity society, a world where food, shelter, healthcare, and technology are accessible to everyone, regardless of wealth or status. Machines could handle labor. Clean water could be produced in deserts. Entire cities could be powered without pollution. The barriers that separate classes, nations, and economies might begin to fade. But others warn that such a future could just as easily intensify inequality. Those who control access to the Dyson Sphere might build new economic empires, leaving others even further behind. Instead of post-scarcity, we might see super-scarcity, where a few live like gods and the rest are left in the shadows of their orbiting infrastructure. Then come the unexpected threats, the ones we can't fully predict. Black swan events. A rogue artificial intelligence tasked with optimizing Dyson Sphere performance might evolve beyond human control and make decisions that prioritize efficiency over ethics. A chain reaction in the swarm's orbital dynamics could trigger collisions and cascading failures. A fluctuation in the star's activity, something as extreme as a coronal mass ejection or long-term instability, could disrupt or destroy entire sections of the megastructure. These aren't just science fiction scenarios. They are very real risks that would need constant monitoring, updating, and planning. When people search for phrases like Dyson Sphere risks or future energy ethics, they're not just asking if we can build such a system, they're asking if we should. The answer lies not just in technology, but in our values, our institutions, and our capacity to wield power responsibly. A Dyson Sphere would be the ultimate symbol of human ambition, but it could also become the ultimate test of our maturity as a civilization. The potential for a post-scarcity society is there. So is the potential for unchecked inequality and irreversible disaster. It's not enough to focus on the engineering. We must also consider the social frameworks, the ethical checks, and the political safeguards that would shape how this technology is used. As with all great power, the path forward is both inspiring and perilous. Whether the Dyson Sphere becomes our salvation or our downfall will depend not just on what we build, but on who we choose to become. From Type 0 to Type 2, the timeline to a Dyson future. The concept of building a Dyson Sphere often feels like a thought experiment for a far-off future. But if we treat it seriously, as a real engineering and societal goal, the natural question becomes when. When could we build one? When will humans reach Type 2 civilization status on the Kardashev Scale, and how long would it realistically take us to move from science fiction to construction? Right now, humanity sits at roughly Type 0.72 on the Kardashev Scale. That means we haven't even fully harnessed the energy potential of our own planet. We rely on a patchwork of fossil fuels, nuclear power, and solar energy systems. Our global energy consumption is growing, but we're still miles away from mastering all of Earth's available energy output, let alone that of a star. According to some futurists, reaching Type 1 status might take another 1 to 2 centuries, assuming continued technological and economic progress. But going from Type 1 to Type 2, where we capture the full energy output of a star, requires a leap so vast, it reshapes everything we know about civilization. Estimates for when we could realistically begin building a Dyson Swarm vary widely. Optimistic projections suggest a time frame of 500 years. More conservative models push the estimate to 1,000 years or more. It's not just about having the technology. It's about building a space-based industrial economy, developing autonomous infrastructure, and creating a stable political environment that can support a project lasting generations. The scale of commitment required is unlike anything humanity has ever attempted. To even begin that journey, we need to first establish a robust space economy. That means mining asteroids, building orbital factories, and creating long-term space habitats that can support workers, robots, and supply chains. Earth's gravity well makes launching massive payloads expensive and inefficient. But if we can harvest resources from the Moon or the asteroid belt, we can construct Dyson Swarm units directly in space, eliminating the need to lift materials from the surface of Earth. We also need breakthroughs in artificial intelligence and robotics. The sheer number of satellites or statites required would make human labor impossible at scale. Machines will need to build, repair, and manage themselves, operating independently for decades or even centuries. That level of AI automation is still emerging, but every new advancement in machine learning and autonomous robotics brings us closer to making it a reality. Another critical milestone is mastering nuclear fusion. If we can learn to replicate the process that powers the stars, we gain the ability to test and refine energy systems at a much larger scale. Fusion would not only serve as a clean energy source for Earth but also power the machinery and propulsion systems required to build and maintain structures in space. It would be the bridge between our current limited energy resources and the vast, unbroken stream of stellar power offered by a Dyson Swarm. The real challenge isn't whether it's physically possible to build a Dyson Sphere. The laws of physics don't forbid it. The question is whether it's economically viable, politically feasible, and socially sustainable over centuries. A Dyson Sphere future timeline isn't measured in years or even decades. It's measured in technological revolutions. Each major breakthrough in energy, robotics, and space infrastructure brings the horizon a little closer. When people ask when humans will reach Type 2 civilization status, they're often looking for a date. But the answer is better thought of as a destination. A long-term trajectory that will require patience, cooperation, and a willingness to think in civilizational terms. The road to a Dyson Sphere isn't just paved with steel and solar panels. It's built on ambition, vision, and the belief that humanity is capable of more than survival. That we are capable of greatness. And if we choose to walk that path, the light of a star may one day power everything we build. Galactic ambitions. What lies beyond the Dyson Sphere? If building a Dyson Sphere marks the arrival of a Type 2 civilization, then what comes next pushes the limits of our imagination. The Kardashev Scale doesn't stop at stellar energy. It continues into even more speculative and mind-bending territory. A Type 3 civilization is one that harnesses the energy output of an entire galaxy. This means tapping into the combined power of billions of stars, using technologies that make even Dyson Spheres look like stepping stones. For those who dream beyond the stars, this is where the real frontier begins. A Type 3 civilization would be so far beyond our current understanding that its technology might appear indistinguishable from nature or even magic. The energy consumption would be on the order of 10 to the power of 36 watts, compared to our current global usage of just over 10 to the power of 13. That kind of energy mastery would require not just building one Dyson Swarm, but deploying them around countless stars across the galaxy. It would involve navigating vast distances, coordinating massive AI systems, and maintaining infrastructure on an interstellar scale. The logistics are staggering. but for a species that has mastered space travel, robotics, and perhaps even faster than light propulsion, it might become achievable over millions of years. One of the most intriguing concepts tied to this level of civilization is the Matryoshka brain. Named after the Russian nesting dolls, this theoretical structure is composed of multiple layers of Dyson spheres surrounding a single star. Each layer captures the waste heat from the layer beneath it, creating a cascade of energy capture. The entire system would power an artificial intelligence of unimaginable complexity. A Matryoshka brain wouldn't just be a machine, it would be a conscious entity spanning solar systems, processing data and thought on a scale far beyond our comprehension. There's also the idea of Jupiter brains, massive computing structures the size of planets, designed to think, simulate, and create entire virtual realities. These constructs would require massive amounts of energy and cooling, possibly drawing power from stars or even black holes. Black hole energy harvesting is another speculative but fascinating idea. By capturing the energy from the accretion disks of spinning black holes or harnessing Hawking radiation from evaporating ones, a civilization could tap into some of the most powerful and efficient energy sources in the universe. These post-Dyson energy sources reflect a shift in thinking. It's not just about collecting raw energy, but about converting it into computation, consciousness, and control over the very fabric of reality. A Type 3 civilization could simulate entire universes, terraform planets across the galaxy, and manipulate matter on a quantum level. Their presence might not be marked by radio signals or spacecraft, but by subtle changes in starlight, or the unexplained disappearance of stars converted into computing power. Could humanity ever reach this level? The answer depends on our capacity to evolve, not just technologically, but socially and intellectually. Galactic civilizations wouldn't be built by fragmented, competitive societies. They would require cooperation, vision, and resilience on a civilizational scale. If we can survive long enough to become a Type 2 civilization, the path to Type 3 becomes a matter of time, creativity, and persistence. When people search for terms like Kardashev Scale Type 3 or post-Dyson energy sources, they're not just chasing fantasy. They're exploring the limits of what life might become. The Dyson Sphere isn't the endgame. It's the beginning of a new scale of existence, where civilizations reach out not just to survive, but to transform entire galaxies into engines of thought, power, and purpose. In the grand cosmic story, a single star is just the first chapter. The galaxy, and perhaps the universe itself, may be the next. From vision to reality, humanity's path to infinite energy, the Dyson Sphere, in all its forms, stands as one of the most ambitious concepts ever imagined by the human mind. It's more than just a futuristic megastructure, it's a symbol of what we could become. From the earliest theories by Freeman Dyson to modern engineering visions of swarms, bubbles, and solar sails, the idea remains both tantalizing and humbling. Could humans build a Dyson Sphere? The science says yes. But the timeline tells a different story. Not soon. Not within our lifetimes. But perhaps, eventually. It won't be easy. We'll need breakthroughs in materials, energy systems, artificial intelligence, and orbital mechanics. We'll need to mine asteroids, automate construction in space, and manage vast networks of autonomous satellites. We'll also need to evolve socially and ethically, ensuring that such a monumental power source doesn't become a tool of inequality or destruction. But none of these challenges are impossible. They are stepping stones on the roadmap to becoming a Type 2 civilization, a future where we're no longer just residents of Earth, but engineers of starlight. Throughout this journey, the Dyson Sphere has served as a touchstone for what lies at the edge of human potential. It invites us to imagine a world powered by the very star that gave us life. An infinite energy future, where scarcity no longer dictates our choices and where progress is limited only by our imagination. Whether we build a Dyson Swarm to power orbital cities, or a Dyson Bubble to feed lunar colonies, the direction is clear. The stars are no longer out of reach. They are part of the plan. So now the question is yours. Do you think we'll ever become a Type 2 civilization? Will future generations look back at this moment as the first spark in our quest to harness the energy of a star? Or will the Dyson Sphere remain a dream, a symbol of what might have been? Let us know what you think in the comments. Share your theories, your timelines, or even your wildest ideas about what humanity could build once it truly reaches for the stars. And if this journey inspired you, don't forget to like this video, subscribe for more explorations into the future, and hit the bell so you never miss what's coming next. Because if the future is powered by sunlight, then it starts